Hello, Assalamu alaikum. Today we are going to talk about output stage and power amplifier. So basically I'm going to cover this topic from these books that have been referred below. So most of the topic will be from the book of Electronic Devices and Circuits by David A. Bell, 5th edition. So before talking about power amplifier, let's try to understand what is power amplifier. So basically a power amplifier is such an amplifier which will provide a power that is greater than 1 watt. So below 1 watt we don't call them as power amplifiers, but above 1 watt we call them as power amplifiers. So if you think about some audio amplifier, audio systems, speaker systems, you'll see that it usually outputs around hundreds of watts. So those are power amplifiers. Again, the mobile phone you're using, it has an antenna and it requires around 1 watt of power. So for that antenna we also require a power amplifier. Sometimes we also drive DC motors, so we also need power amplifier for those situations. Okay, so to summarize, the main thing that power amplifier or audio amplifier or large signal amplifier develops relatively large output voltages across low impedance loads. Again, this last word, that is low impedance loads, typically you see in the small signal amplifiers before that we have studied, like common source amplifier and vice versa. So in those amplifiers the values of the loads were in kilo ohms, right? So basically we would get milliamperes of currents in the drain or collector side or in the output. So the power level was low and the current level was also low. But right now, if we talk about a speaker, if we want to drive a speaker, a very common speaker resistance rating is 8 ohm. So definitely it will require a larger current, so a very low resistance. So for this low resistance, so this low resistance load, when connected to the say output of the amplifier, will degrade the performance of the amplifier definitely due to the loading effect. Okay, that is the impedance mismatch with the output resistance of the amplifier. So that's why we require large signal amplifier. So again, if we want to apply large signal directly to the amplifier, then what will happen is we know that it will cause non-linearity. So that signal at the output won't be usable. So that is another problem. So these are some of the problems that we need to address. So to overcome these problems, what we do is we use multi-stage amplifiers. Instead of using single stage, we use multi-stage. Say for example, in the first stage we may use a simple voltage amplifier, small signal voltage amplifier. In the second stage again we can use a small signal voltage amplifier. So multiple levels of small signal voltage amplifier. And in the last stage, that is the final or the drive stage, we will use a large signal amplifier or audio amplifier or a power amplifier that will provide a very high power. So typically BJTs are more capable than MOSFETs in terms of dealing with higher currents. That's why we will be choosing BJT here. So again, by using output stage, one of the things we can achieve is that we can alleviate the problem of impedance matching too. So mismatch of impedance, we can also reduce that effect. So what are the typical loads of power amplifiers? We already talked about this. Motor, antenna, speaker are the typical loads. So basically the requirement of power will be from 1 to several hundreds of watts. In market there are hundreds and hundreds of watts of amplifiers that are available. Okay, so So there are various ways that we can couple the load with the amplifier. One of them is directly coupling the load. That will give the best performance in terms of efficiency, but there is a problem or downside to it, that it requires both the plus and minus VCC. So two supply signals will be required in that case, a positive one and negative one. So this is the downside. And the very popular is this capacitor coupled, because we have been doing the capacitor coupling in the previous small signal analysis or small signal circuit designs, right? So but the problem with the capacitor couple is that it may give isolation to DC signals, and but the problem with this capacitor coupling will be that it will create problem during the impedance matching, because the load is of low resistance, right? So the last one is the transformer coupled. So the transformer coupled is actually the best suited for impedance matching. As you all know, that transformer has primary and secondary side, so you can use the turns ratio and reflect the low resistive load towards the amplifier into a high resistance. So these are some of the advantages that you will be getting from doing the transformer coupling. On top of that, it will also provide you with the DC isolation. So we'll be talking about transformer coupled load. So if we talk about classification of power amplifier, typical classifications are class A, class B, class AB, and class C. So this picture here shows the class A amplifier, where you can see that this is the collector current of BJT, and full signal is being conducted through the BJT. So 360 degree the BJT is conducting the full signal, so 360 degree conduction is achieved. For the second figure, that is class B, you can easily see that half of the time the BJT is on, so this is just 180 degree of conduction achieved. And for class AB amplifier, you can see it's just slightly more than half of the time of conduction of BJT has been achieved, so just a slightly more than 180 degree. And the last one is a class C amplifier. So usually that conduction is less than 180 degree, as you can see. So an interesting thing about class C amplifier is that we transmit the power using the resonance concept here. And there is another very highly efficient class amplifier, that is class D amplifier. So that is a very high fidelity, highly efficient amplifier. So let's talk about transformer coupled class A amplifier. This is the circuit of the class A amplifier, and you can see that the load, this RL load, has been coupled by transformer. This is the N1 is the primary turns ratio, N2 is the secondary turns ratio, or the turns number, and R1 or R2 are the biasing resistors. RE is the emitter resistors, which will control the emitter current or the BJT current. Okay, so and this is a bypass capacitance. This will short the resistance in AC. Okay, so this will create a short path to ground in AC analysis. So for DC or biasing, the DC current will see this RE resistance, but for AC current, this is shorted to ground. Okay, emitter is shorted to ground. So so the Q point of class A amplifier is usually selected at the center of the AC load line. Okay, so this type of power amplifiers usually have low efficiency. The maximum theoretical efficiency is around 50%, and we use it for low power applications. So some of the design expressions that we need to remember is that DC resistance, AC resistance, and the efficiency. So the DC resistance means the primary resistance primary winding resistance plus the emitter resistance will give you the RL DC. RL AC is the this RL load will be reflected towards the primary side by using this formula, as you can see. So RL plus RPY is the primary winding resistance and RL is the reflected load. So see that we have used this reflected load equation, N1 divided by N2 whole square into RL plus RPY. What happens, you will see later on, that this low resistance value will be reflected towards the collector side, and the value of the reflected load will increase tremendously. Okay, so this is the AC resistance and this is the DC resistance. DC resistance will be required to calculate the bias point or the Q point, and also will be required to draw the DC load line, and AC resistance will be required to calculate the AC load line. And the efficiency of the transformer is output power divided by input power into 100% basically. So that's what it is. Now moving forward, so let's talk about a problem. So the problem says we need to draw the DC and AC load lines for a class A circuit, given that the supply voltage is 13 volt, primary resistance, see that it is ohms, very low resistance, basically primary resistance of the primary winding resistance. R1 and R2 are the biasing resistance in the kilo ohm range. RE is the emitter resistance, N1 and N2 are the transfer ratios. Also calculate the efficiency of the circuit. So we need to also calculate the efficiencies of the circuit. Assume that the transformer has an efficiency of 80%. So the transformer is not an ideal transformer, it has an efficiency of 80%. So as you can look at the circuit, you can easily find, we know the value of R1 and R2 and VCC. Easily we can find the value of VB by using the voltage divider rule. That has been done here, and we get the value of around 5.7 volts. So what we have done here, we are just considering the base current to be very small, that it will rarely impact the emitter current. To ease up the calculation, what we are assuming is that the emitter current is equals to the collector current. Basically the actual equation goes something like this, that emitter current is equals to base current plus collector current, but as the base current is very small, we will be considering that emitter current and the collector current is same. So what we are finding here is collector current is equals to emitter current is equals to 5 milliampere. This comes from this. So see that as we have the base voltage as 5.7, and to turn on the BJT, base to emitter voltage should be 0.7, so you can get the emitter voltage, and with the help of the emitter voltage and this emitter resistance, that is 1 kilo ohm, so emitter voltage becomes 5 volts. 5.7 minus 0.7, you get 5 volts at the emitter, divided by 1 kilo, you get 5 milliampere as emitter current and collector current. Now then we proceed on to calculate the VCE, that is the collector, this is the collector point and this is the emitter point. So collector to emitter voltage, that is the Q point. Q point, we want to calculate the Q point. So one value of the Q point has been calculated, that is IC, and the voltage of the Q point is VCE. So VCE can be measured by, so this is the supply voltage minus the drop across this one, that is primary winding resistance, right, and then the drop across this emitter voltage drop, right. So see that this has been done here. VCE is equal to VCC minus IC into RPY will give you the drop across the primary winding resistance, and IC times RE will give you the emitter voltage drop. So in totaling this or calculating this, we get 8 volts, around 8 volts. So now we have the Q point. So the Q point is actually 5 milliamperes comma 8 volt. Okay, so this is the Q point. You can see this is 5 milliamperes, and the voltage spectrum, it is 8 volt. Now let's try to find out, we need another point to calculate the DC load line. So in order to do so, what we are doing is we are inputting IC is equals to 0 in this equation. So by doing so, we get that the VCE is 13 volt. So this gives us another point. So when the IC is equals to 0, this means this line, at this line, that is in the horizontal axis, right? The point will be on the horizontal axis when IC is equals to 0. So VCE is equals to 13 volts. So you see VCE is equals to 13 volts. That means this is the point, this is the another point. Now you have 2 points basically. One is the Q point, another one is the this point. That is the in between 12 and 14 volt. That is the 13 volt point. This is a red marker. Now just draw a line using this 2 point and proceed or extrapolate. So you get this solid line, which is the DC load line. So I have marked here, this is the DC load line. You see, this is the DC load line. So you draw the line between using this 5 milliampere 8 volt and 0 milliampere 13 volt point. You get the DC load line, this solid line. Now in order to find the AC load line, you need to calculate the AC another point, that is the AC point. Okay, so how can we do that? By using the AC resistance, right? So here we have used the DC resistance. Now we will be using the AC resistance. So we need to calculate the AC resistance. Now one thing you should see here is that the load resistance, somewhere I have missed out on the load resistance value here. I guess it is 56 ohms. Okay, the load resistance value is 56 ohms. Let me just write it down so that you can remember. It is around 56 ohms. So RL was given, it was around 56 ohms. Okay, so it was 56 ohms. And okay, so with the so see that it is in the ohm range, so the load resistance is very low. So by using the transformer coupling, what we are doing is we have reflected the load by using the equations, and now you see the new resistance, that is the resistance seen by the amplifier, is very high, 1.6 kilo ohms, right? It's now in the kilo range. So this gives us a benefit. This is a big benefit of transformer coupling. Okay, so now moving forward, by using this equation, we find the reflected load or the AC load. Now by using this AC load, we will be calculating our AC, one of the AC points. Now when del IC is equals to 5 milliampere, that is the change in current is 5 milliampere. Why we are saying that the change in current is 5 milliampere? Because the DC load line stays here. Now if you look at the current value of the DC, it stays at 5 milliampere. So if you give a AC signal, it goes down to maximum 5 milliampere, right? After that it will turn off the BJT. We don't want it to happen. So basically the change of current in AC, it will be a sinusoidal wave, right? Or some AC wave, right? So that may go to 5 milliampere maximum, but not more than that. So that is why we're saying that del IC is equal to 5 milliamperes, and del VCE now can be calculated by using this equation, that del IC times our AC load. So del IC times our AC load is equals to, we get 8 volt. The value is 8 volt. Now so now we have del VCE, that means change in collector to emitter voltage is 8 volts. Previously the Q point is in 8 volt. Now on top of that you are having a swing of 8 volt, additional swing of 8 volt, change of 8 volt. Now if you add towards your right hand side from 8 to 8, you get 16. Okay, you get 16. So basically what we are getting here is another point, that is the AC point. So this will give you the AC point. This 8 volt you have to add with the bias point voltage, VCE voltage, to get the new AC point. Now with the help of this AC point and the Q point, draw a line to get the AC load line. This is the dashed line or dotted line is the AC load line. Okay, so these are the two important load lines we need to figure out. Now let's talk about the efficiency of the transformer. Now the, about the efficiency of the transformer, it's very straightforward because this is the circuit. So the input power is basically the supply voltage times the collector current. So what we have here, the supply voltage is 13 volts and the collector current was 5 milliamperes. If you multiply 13 by 5, you get 65 milliwatts. Okay, now what is the output power now? Now the output power is transformer efficiency times the output power basically. Okay, output power dash. So what is this output power dash? So the transformer efficiency was given as 80%, so we have written the transformer efficiency. What is the output power dash? Output power dash is the power without the transformer efficiency. So it is not that difficult to calculate. It's half times Vp into Ip. So what is Vp? The peak voltage of the AC signal, and Ip is the peak current of the AC signal. Now this is very simple to find out because the peak voltage of the AC signal will be 8 volt and the peak voltage of the AC signal, peak current of the AC signal will be 5 milliampere, right? So that's what it is. So the 8 volt and 5.5, 0.8, you get 16 milliwatts. So this is the total output power. You're giving 65 milliwatt, but you're getting at the output is only 16 milliwatts. So what is the efficiency now? Output power divided by input into 100%. So you do this, you get only 24.6%. But practically what will happen, you'll get much lower efficiency. Now what's the solution to this? So very low efficient class A amplifier, right? The solution can be found in the next type of amplifier, that is class B amplifier. The circuit is a bit complex in corresponding with the previous one, as you can see that. Okay, so in this particular circuit, again we are using the transformer coupling, but now you can see that we are providing a VCC signal or the supply signal in the center tap of the primary side. In the secondary side you have your RL as usual. Now you're using two NPN BJTs and we are making the emitter grounded, and there are two biasing resistance R1 and R2. See that there is no DC biasing voltages. So what will happen, for the only positive portion here, this transistor will work. For the only positive portion here, this transistor will work. So this transistor will work for the only positive half cycle, providing this, and this transistor will work for the negative half cycle, for this second positive half cycle, so providing this. These two will combine at this primary side and it will give a full signal at the output. So 180 degree time 180 degree conduction will be achieved by this one, and other 180 degree conduction will be achieved by this this second transistor. This is how your class B amplifier works. Interesting thing is that how we have increased the efficiency. See that we don't need any DC power. Previous example shows you that the maximum power that we have dissipated was from the DC supply in order to bias the transistor, but now we don't need that. So that's why the efficiency has increased, and it has increased to around 79%, more precisely 78.6%. okay, so basically these two transistors are cut off at are biased at cutoff region. So this concludes my today's topic on lecture topic on power amplifiers. Thank you.